Hi everyone! This video is a brief tutorial into the wonderful world of astroseismology through the lens of our new open source package pySYD. If you run the help command, you'll see that pySYD has a handful of different modes, but today we will only be using our run feature. As you'll see, there are an enormous amount of options for this feature, which looks terribly overwhelming, but these are here for good reason, and that's to provide the best possible results on a star-by-star basis. So let's walk through some of these. We'll start by running kick 1435467 and show both the verbose outputs and plots. By default, this will run a mini module that estimates where new max is before deriving any parameters. The bulk of the heavy lifting is done in the second part, shown by this very busy figure here. And keep our other video for a nice explanation of what this figure is showing. In fact, you'll see that there is another window hiding behind this that shows the results from the optional module that estimates new max. You can see the signature due to power excess due to solar-like oscillations, and you can see them on the bottom plot there that did a nice job of finding them. And now for the background fitting part, I'd like to also include the BIC and AIC information for each of the models that pySYD iterates through. So essentially the same as last time, but just with this additional output. And in fact, to test whether we like the model that pySYD is selecting, we can use this Boolean flag, which will output some of our developer plots that will show our initial guesses for the background model and all of the models that it iterated through, and then it will highlight the selected one so we can see if we actually, if we like the model that pySYD is selecting. Yes, so here is that figure, and you can see that again, we have our initial guesses here, and then it shows how many laws are used and if the white noise was fixed or free, and then it highlights our model there. And in this case, it didn't select the most complicated model, so it's behaving as we hope. Okay, so now we'll move on to a more evolved star, a subgiant whose shell diagram actually doesn't look as straight and ridgy as we'd hope. But it turns out that if you have a rough idea of what d nu is, or our characteristic frequency spacing, and an interval of the folded power spectrum here, it's from 2 to 22 with an expected d nu of about 36. What it can do is whiten or essentially wash out what we call mixed modes, so you can better estimate your characteristic frequency spacing. And sometimes this is referred to as notching. You can see the feature both in the power spectrum. Now it looks more clear with the spacing. We have less peaks in the autocorrelation function, and it turns out it actually liked that spacing anyways. Okay, and now for our most evolved example, let's take a quick peep at what the power spectrum for the more evolved star looks like. So we're just going to go back to our two basic Boolean flags, show and verbose output. Let's see what these look like. Yikes. So you can see that with our default smoothing filter, box filter that we use for higher new maxes, it actually was making the power spectrum look really odd. So we can actually turn off that smoothing filter by using 0 and see in the middle panel that this provides, looks much better. But if you look at the shell diagram, it looks like some of the orders are cut off on the bottom, so we can actually change the number of orders that the shell diagram displays by number in the y direction or number of orders, and change that to 9. And now we'll see what the shell diagram looks like, and you can see it looks much better here. Okay, now to get a little more creative. Say, for example, you care less about the global seismic parameters, nu max and d nu, or that you are a researcher studying cool stars to where you wouldn't be able to detect the p mode oscillations, but still care about and want to measure the background parameters, or the timescales and amplitudes for which different granulation processes are occurring. As I said before, the optional first module, the mini module that estimates nu max, can be turned off by using the Boolean flag x, which is true by default, and same with the global parameters, or G. So we can disable these if we are only interested in the background. Let's say, for example, that you'd like to compare to some previous results that use maybe just 2 Harvey components instead, and you would like to fix the number of Harvey laws it uses. It'll still iterate between the 2 models that are possible, which is fixing the white noise or adding that as an additional free parameter. But we can also fix the white noise if we want, and then you'll see that it doesn't do any model comparison since we fixed both of these main properties. In fact, we can also fix the white noise by using the single Boolean flag, where here we didn't fix the number of Harvey components and it still iterated through the 3 different models. And now for all of these cases, we have not yet determined any parameter uncertainties. So our flag, MC for Monte Carlo sampling, by default is 1, so we'll only run a single iteration. But if we set that to something, say, like 200, which should be more than sufficient for this bootstrapping uncertainty estimation, then you can see in the output parameters that they have uncertainties now. So thanks for tuning in.